21.91 is another electrostatic problems with hanging masses. First, let's define our positive direction to be upwards. The thing is that we don't know what is the sign of this charge, of this sheet of charge. It can be positive or it can be negative. So just to be consistent, it's always a great idea to have defined a positive direction and stick to that. So in fact, we are supposed to calculate the direction of the electric field in part A. So let's see what kind of forces we have acting on this mass. So there's going to be gravity mg down, and it's suspended on a string, so there's a string tension force upwards, and then there's also the force from this sheet of charge, the Coulomb force. We don't know which direction it's going to be, so we just guess that it's going to be upwards. And if we balance this mass, it means that the forces have to cancel each other. So we have tension force plus the Coulomb force must equal the gravity. And we want to solve for the Coulomb force because from that we can tell which direction the electric field is pointed. Fc, Coulomb's force, equals mg minus t. And the Coulomb force, as always, can be expressed as the product of the electric field and the test charge, in this case, charge Q. This equals mg minus t. Solving for E, we get mg minus t divided by Q. The mass is 0.18 kilograms, G 9.81 meters per second squared. The tension force was known to be 4.96 newtons. And the charge 0.305 times 10 to the minus 6 coulombs. This gives us about minus 1.05 times 10 to the 7 . And the new units are, yes, newtons per coulomb. Let's make that clear. So from here we see that our electric field is in fact negative. So it's in the opposite direction what we indicated here. So we know that the electric field must be downward. And here is the magnitude of the electric field, which also answers the question in part B. In part C, we are supposed to calculate the surface charge density of this sheet, which is considered to be of infinite length. So we already knew that because the electric field is downwards, E goes this way, then the sheet must be negatively charged. The electric field of any uniform sheet is given as E equals the surface charge density divided by 2 times epsilon 0. And this is a very important result. It is shown in the book and it applies to a lot of situations, so this is one worth remembering. from here we can solve the charge density to be electric field magnitude times 2 times E0, and we had for the electric field magnitude, no negative sign included, 0.1.05 times 10 to the 7 newtons per coulomb times 2 times E0, which is 8.85 times 10 to the minus 12 coulomb squared divided by Newton m squared. One of the coulombs cancel, the newtons cancel, so our units are coulombs per square meter, and the actual magnitude is 1.85 times 10 to the minus 4 coulombs per square meter, and the charge was negative, but this is the magnitude of the surface charge density in this case.